From space, Earth appears simple, a vibrant marble of blue oceans and green-brown continents divided by land and sea. But beneath this beauty lies a profound difference. Two types of crust, oceanic and continental, each with its own story. This hidden dichotomy drives the forces that shape our world. Join us as we peel back the layers and explore the engine beneath our feet. The story begins over 4.5 billion years ago. Earth was a molten sphere, a chaotic world of incandescent magma. As it cooled, a thin, fragile skin solidified, forming the oceanic crust. Dense, iron-rich basaltic rock formed this thin, heavy crust. Water vapor condensed, creating the first oceans. Volcanic activity at tectonic boundaries forged lighter, complex rocks. These rocks, like granite, formed thicker, stable landmasses. Proto-continents emerged, the ancient cores of today's continents. This created two distinct crust types, oceanic and continental. Oceanic crust is thin and dense, recycling back into the mantle. Continental crust is thick, buoyant, and preserves ancient history. Earth's crust is split into two worlds, oceanic and continental. Oceanic crust is born at mid-ocean ridges, spreads and is recycled in fiery subduction zones, never lasting more than 200 million years. Continental crust, thick and buoyant, resists destruction, preserving Earth's ancient history. This cycle of renewal and permanence drives plate tectonics, building mountains, fueling volcanoes and shaping the ever-changing face of our planet. Over 4.5 billion years ago, Earth was a molten, chaotic world, shaped by relentless asteroid impacts and searing heat. Heavy metals sank to form the core, while lighter minerals rose, creating the planet's layered structure. As Earth cooled, a fragile crust formed above the magma, marking the birth of solid ground. This unstable crust was the first step toward the continents and oceans we know today. Out of the chaos of the Hadean Eon, Earth's first stable crust formed, oceanic in character, made of dense basalt from mantle melting. Rapidly cooling lava created a resilient, thin shell covering the planet, forming the primordial seafloor. Torrential rains filled lowlands, creating Earth's first global ocean, a vast water world above a uniform crust. This dense crust was recycled by the mantle, beginning the cycle of creation and destruction that shapes our oceans today. The emergence of land from the global ocean was not a single event, but a gradual, protracted process that unfolded over hundreds of millions of years. The key to forming continental crust lay in a new geological process, subduction. As the early oceanic plates moved across the planet's surface, they inevitably collided. In these collision zones, the colder, denser plate would bend and sink back into the mantle. As this descending slab of water-rich oceanic crust plunged into the hot mantle, the water it carried was driven off. This water lowered the melting point of the overlying mantle rock, causing it to melt and generate a new type of magma. This new magma was fundamentally different from the basalt that formed the ocean floor. Through a process known as magmatic differentiation, this secondary melt was even more enriched in silica and lighter elements like aluminum, sodium, and potassium. This felsic magma, being less dense and more viscous than basaltic magma, rose towards the surface but did not always erupt. Instead, it often pooled and cooled slowly beneath the surface, forming large bodies of granitic rock. Where it did erupt, it created chains of explosive volcanoes that rose above the ocean's surface, forming the first volcanic island arcs, similar to modern-day Japan or the Aleutian Islands. These island arcs were the seeds of the continents. They were small, isolated landmasses built from lighter, more buoyant rock than the surrounding oceanic crust. Because of their lower density, they resisted being pulled back down into the mantle through subduction. Instead, when these island arcs collided with each other due to the continuous movement of the tectonic plates, they didn't sink. They merged, welding together to form larger and more stable blocks of land. This process, known as accretion, gradually assembled small volcanic islands into larger microcontinents, the first truly stable pieces of continental crust. These early landmasses, or proto-continents, were not the sprawling continents we see today. They were likely smaller, hotter, and more geologically active. However, their very existence marked a revolutionary change for the planet. For the first time, there were two distinct types of crust: the dense, low-lying oceanic crust and the buoyant, high-standing continental crust. This duality was the critical innovation that would allow Earth to develop the complex tectonic system that defines it. The rise of these first landmasses broke the uniformity of the global ocean and set the planet on a new evolutionary path towards the world of continents and oceans we inhabit. The fundamental difference between oceanic and continental crust is ultimately a story of magma chemistry. The journey begins in the Earth's upper mantle, a region of hot solid rock known as peridotite. When this rock undergoes partial melting at a mid-ocean ridge, it produces a mafic magma. Mafic refers to its high content of magnesium and iron, which yields dark, dense minerals. This magma is fluid and hot, allowing it to flow easily and erupt non-explosively onto the sea floor. Upon cooling, it solidifies into basalt, the fine-grained volcanic rock that forms the upper layer of oceanic crust, and gabbro, its coarse-grained equivalent that cools deeper down. This primary differentiation creates a crust that is geochemically simple and relatively uniform. Oceanic crust is a direct, first-generation product of mantle melting. Its composition closely reflects its source, albeit enriched in the elements that melt more readily. This direct lineage is why oceanic crust is so consistent in its makeup across the globe. It is a simple, two-layer system of basalt and gabbro, thin and dense due to its iron and magnesium-rich mineralogy. This geochemical signature is the reason it sits low, forming the deep ocean basins, and is dense enough to be readily subducted back into the mantle from which it came. The creation of continental crust, however, involves a far more complex, multi-stage refining process. It begins when water-rich oceanic crust is subducted. The water released from the sinking slab triggers melting in the mantle wedge above it. But this is only the first step. The resulting magma rises, melting and assimilating parts of the overlying crust as it ascends. This process, known as assimilation and fractional crystallization, progressively changes the magma's composition. Heavier, iron-rich minerals crystallize and sink, leaving the remaining melt increasingly enriched in silica and lighter elements like potassium and sodium. This creates a highly evolved felsic magma. This felsic magma, rich in silica and feldspar, is the building block of continents. When it cools, it forms rocks like granite and granodiorite. These rocks are packed with light-colored minerals like quartz and feldspar, making them much less dense than basalt. This intricate multi-step process is like a planetary-scale distillery, progressively refining primitive mantle material into a buoyant, silica-rich concentrate. It is this complex geochemical journey from mantle peridotite to basalt, and then through subduction and remelting into granite, that creates the profound chemical and density difference between the two types of crust, giving continents their characteristic buoyancy and permanence. With the birth of these two distinct crustal types, the geological destiny of Earth was set. The planet was no longer a homogeneous water world with a uniform basaltic shell. It had developed a fundamental dichotomy: dense, recyclable oceanic crust, and buoyant, permanent continental crust. This duality became the primary engine for plate tectonics, the grand unifying theory of geology. The continuous creation of oceanic crust at mid-ocean ridges provided the pushing force, while its destruction at subduction zones provided the pulling force, driving the plates across the planet's surface in a slow, relentless dance. The continents were carried along for the ride. The physical differences established during their formation dictated their interactive roles for the rest of geological time. Oceanic crust, being thin and dense, would always be the subordinate plate in any interaction with a continent. Its destiny was to form in fire at a ridge and be consumed in fire at a trench, ensuring its geological youth. Continental crust, thick and buoyant, became the resilient passenger. Unable to sink, it floated high on the mantle, preserving rocks and geological structures for billions of years. When continents collided, they would not be destroyed but would instead crumple and thicken, pushing up the planet's great mountain ranges. This new dynamic system had profound implications for the planet's evolution. The process of subduction and continental volcanism continuously released gases from the planet's interior, shaping the long-term composition of the atmosphere and oceans. The erosion of the high-standing continents delivered vast quantities of sediment and dissolved minerals into the oceans, altering seawater chemistry and providing the raw materials for sedimentary rocks. This interplay created feedback loops that would go on to influence global climate, nutrient cycles, and the very course of life's evolution over billions of years. The birth of the two crusts was not just a geological event, it was the foundational change that made Earth a living, breathing system. Thus, the story of the birth of crust is the story of how Earth became the unique planet it is today. The initial cooling and differentiation created the potential for a crust. The primacy of mantle melting established a global oceanic plate. Finally, the magic of subduction zone chemistry allowed for the creation of buoyant, permanent continents. From this point forward, the history of our planet would be written in the interactions between these two surfaces, one ephemeral and one enduring. This dynamic tension, born in the planet's fiery youth, set the stage for the mountains, oceans, earthquakes, and volcanoes that continue to shape our world. Oceanic crust is young, constantly renewed at mid-ocean ridges and destroyed at subduction zones. Continental crust, however, is ancient, preserving Earth's history for billions of years. It accumulates and grows, never subducting, forming great mountain ranges. Continental crust is Earth's permanent, ever-growing memory stick. Density is the key to why oceanic crust sinks and continents float. Oceanic crust, made of dense basalt, is heavier than the lighter granitic continental crust. This small difference means continents ride high, while oceanic plates subduct beneath them, fueling volcanoes and building land. Without this, Earth would be a flat, watery world. Density shapes our planet's very surface. Oceanic crust is like a layered cake. Sediment, pillow basalts, sheeted dikes, and gabbro, formed simply and predictably at mid-ocean ridges. In contrast, continental crust is a chaotic patchwork, thick, diverse, and assembled over billions of years through collisions, intrusions, and endless recycling, preserving a complex record of Earth's history. Oceanic crust is mafic, dark, dense, rich in iron and magnesium, born directly from the mantle. Continental crust is felsic, light, buoyant, silica-rich, and the product of countless cycles of melting and reassembly, making it chemically complex and evolutionarily refined. Oceanic crust is a conveyor belt, created at ridges, travels across the seafloor, and is recycled at subduction zones, always young and fleeting. Continental crust is an archive, assembled over eons, rarely destroyed, and preserves the deep, intricate history of our planet. Where oceanic and continental crust meet, subduction triggers deep trenches, explosive volcanoes, and massive earthquakes. Nowhere more dramatic than the Pacific's Ring of Fire, where the planet's most powerful geological forces are unleashed. When continents collide, neither can sink, so the crust crumples and thickens, thrusting up colossal mountain ranges like the Himalayas and Alps, preserving a dramatic record of tectonic power and the resilience of continental crust. When two oceanic plates collide, one subducts, forming deep trenches and volcanic island arcs, dynamic chains like the Marianas in Japan where new crust is born and evolves, offering a glimpse into the making of continents. Plate tectonics isn't just about plates colliding, it's also about them moving apart. At mid-ocean ridges, magma rises, creating new seafloor and widening oceans. The Mid-Atlantic Ridge is a prime example, splitting the Atlantic and forming new crust. On land, rifting can split continents, as seen in the East African Rift, which may one day become a new ocean. The interactions between Earth's plates, driven by the fundamental differences between oceanic and continental crust, are the master engine of global change. These tectonic processes operate on a planetary scale, constantly reshaping the surface of our world in a slow but relentless ballet. The configuration of continents and oceans that we see today is really just a temporary snapshot in geological time. Over millions of years, subduction consumes entire ocean basins. Continental collisions raise and then erode mountain ranges, and rifting creates new seas. This dynamic system dictates the very geography of our planet, controlling the location and shape of every landmass and ocean. This continuous motion has profound and far-reaching consequences for the entire Earth system, extending well beyond simple geology. The arrangement of continents, for example, is a primary control on global ocean circulation patterns. When continents block equatorial flow or open up gateways around the poles, it dramatically alters how heat is transported around the planet, which in turn has a major impact on long-term climate. The uplift of massive mountain ranges like the Himalayas and the Tibetan Plateau can change atmospheric circulation patterns, creating powerful monsoon systems and arid deserts in their rain shadows, affecting the climate and ecology of entire continents. Furthermore, plate tectonics is intimately linked to the planet's carbon cycle and, by extension, its long-term habitability. Volcanism, which is most active at plate boundaries, releases carbon dioxide from the Earth's interior into the atmosphere. Conversely, the weathering of silicate rocks, especially in newly uplifted mountain ranges, draws carbon dioxide out of the atmosphere. The subduction of oceanic crust carries carbon-rich sediments deep into the mantle, locking it away for geological timescales. This intricate feedback system, mediated by plate tectonics, has helped regulate Earth's climate over billions of years, keeping it within a range suitable for life. Ultimately, the action of plate tectonics is the reason Earth is a living, breathing planet, rather than a static dead rock like Mars or Mercury. The constant recycling of crust, the outgassing of volatiles, and the creation of topographical diversity are essential for maintaining the conditions that allow life to thrive. The interaction between the ephemeral, sinking oceanic plates and the permanent, floating continental plates is the heart of this system. It's a powerful, creative, and destructive force that has sculpted every feature of our world and will continue to drive its evolution for billions of years to come, long after our own maps have become irrelevant. The ocean floor, built on oceanic crust, is a surprising source of valuable minerals. Volcanism creates hydrothermal vents, where superheated water forms rich deposits of copper, zinc, gold, and more. Manganese nodules and crusts, loaded with metals for modern technology, grow slowly on the abyssal plains. Yet, as the oceanic crust is recycled by subduction, these resources are both created and destroyed in a never-ending cycle. The continental crust is humanity's treasure chest, holding vast mineral and energy wealth. Its ancient, complex history has concentrated gold, uranium, iron, copper, and rare earths, as well as fossil fuels like oil and gas. Even diamonds are gifts of deep, ancient crust, brought to the surface by rare volcanic eruptions, linking our most coveted gems to the oldest, most stable parts of our planet. The origin of life may be tied to the differences between oceanic and continental crust. Deep-sea hydrothermal vents and volcanic hot springs on land both offered unique conditions: energy, minerals, and chemical building blocks. Perhaps life began in one or both of these settings. The dynamic interplay of Earth's crust created the diverse environments that made life possible. Earth's oceanic and continental crust work together to regulate the planet's climate and keep it habitable. Oceanic crust sequesters carbon deep into the mantle, while continental crust draws down atmospheric CO2 through weathering. This cycle acts as a planetary thermostat, balancing greenhouse gases and supporting life. Without both crusts, Earth would not be the rare, life-friendly world it is today. Where oceanic and continental crust collide, Earth's most violent hazards are born. Subduction zones generate massive earthquakes, tsunamis, and explosive volcanoes, threatening cities like Tokyo, Santiago, and San Francisco. The infamous Ring of Fire is a direct result of this ongoing battle deep beneath our feet. Living on these margins means facing the constant threat of nature's most powerful forces. While plate collisions build mountains, rifting tears continents apart, creating deep valleys, earthquakes, and volcanoes. The East African Rift shows this process in action. Land is stretched, fractured, and reshaped by powerful forces. Eventually, rifting can create new seas, as happened with the Red Sea and even new oceans. The world's map is always changing. Today's hazards are tomorrow's oceans. The movement of tectonic plates shapes not just continents, but Earth's climate itself. When supercontinents like Pangaea form, they create extreme climates and vast deserts. As they break apart, new oceans and coastlines appear, moderating the climate and boosting biodiversity. This grand cycle, driven by the properties of oceanic and continental crust, is Earth's ultimate climate control. The geological drama shaping our planet is far from over. Tectonic plates drift, continents shift, and over millions of years, Earth's map will be redrawn. In about 250 million years, scientists predict the continents will merge into a new supercontinent, perhaps Pangaea, Ultima, or Amasia. A single colossal landmass will dominate, surrounded by a vast global ocean. The continents endure while the ocean floor is erased. As continents converge to form a new supercontinent, the oceanic crust is destroyed, but the continental crust endures. The continents are Earth's great survivors, carrying the memory of our planet's history. New mountains will rise, built from the crumpled edges of today's continents. This duality, one crust ephemeral, the other eternal, defines Earth's ever-evolving story. Earth's surface beauty hides a profound secret. Two fundamentally different crusts shape our world. Oceanic crust is young, dense, and recycled. Continental crust is ancient, thick, and enduring. This duality drives plate tectonics, mountains, earthquakes, and the resources we depend on. The story of two crusts is what makes Earth uniquely alive. The ground beneath our feet is more than just solid land. It is a library of time, a dynamic engine, and the foundation of our existence. The differences between the dense, recycled oceanic crust and the buoyant, permanent continental crust are etched into every landscape, every mountain, and every shoreline. This knowledge is not merely academic. Understanding these fundamental geological processes is critical for our survival and prosperity. It allows us to predict and mitigate the hazards of earthquakes and volcanoes, to locate the resources needed for our modern society, and to appreciate the delicate balance that maintains our planet's long-term habitability. The story written in the rocks is a story of immense power and unimaginable timescales. Continents drift, oceans are born and die, and supercontinents assemble and break apart in a cycle that has repeated for eons. We are living in a brief, dynamic moment in this ongoing planetary saga. The forces that created the continents and oceans are still at work today, slowly but surely reshaping the world for future generations. By studying the architecture of the crust, we can read the history of our planet and, in doing so, begin to forecast its distant future, envisioning the world of Pangaea Ultima. From the fiery birth of the first crust in a molten primordial world to the slow, relentless dance of the tectonic plates today, the tale of oceanic and continental crust is a story of contrast and connection. One is forever young, the other ancient. One is consumed, the other preserved. Together they have created the world we know, a planet of extraordinary beauty and complexity. Exploring this hidden world reveals not just the secrets of rock and fire, but the very essence of how our planet works, how it has evolved, and why it remains a vibrant oasis in the cosmos. The next time you stand on a mountain peak or gaze out across the ocean, remember the immense and powerful story that lies beneath the surface. Remember the sinking slab and the floating stone. This hidden duality is the foundation of our world, the invisible engine that has shaped all of our past and will define all of our future. Unlocking the secrets of Earth's crust is key to understanding our place within this grand geological narrative. The journey into the heart of our planet is a journey into the heart of ourselves.